Okay, so can y'all see my screen share? This?
Yeah.
Yeah, okay. So for right now, I would like y'all to work on this warm-up. So we have a 3-variable, 3-equation problem. Write this guy as an augmented matrix and solve it using matrix operations. And also start by solving this with your calculator, just so that you know what it is that you are working towards in terms of the answer. After that, we'll go over it. And then today we'll be talking about a new section. Today we'll talk about solving matrices by using inverse matrices. Also, once we get everybody in, I want to do a quick SAT update. I said I would post one over the weekend because on Friday, the College Board had a online meeting to discuss what the changes were going to be for the SAT. I didn't bother typing anything up because they still sound like they're still very much in the air in terms of what their final decision is going to be. And I bet they won't have a quote-unquote final decision. It's just going to be them updating like month by month what the deal is as the viral outbreak progresses and governments respond accordingly. So yeah, I'll just go ahead and start with that now, and we'll start the problem basically right away because you know, I was late to get this going. I'm obviously super tired and just got up. You know that's the case if I didn't pomade my hair. So in terms of the SAT, I think it's currently postponed for them to not restart until July, but in my personal opinion, that's probably overly optimistic. I could easily see it not realistically reopening until August or September, mostly because like they could do it if they could guarantee social distancing at testing centers. So they already spread you out anyway, but that means they would also need to outfit proctors with masks or whatever, and all of that just seems ridiculous. That might happen, but I doubt they could actually set up the infrastructure to conduct the testing like that. When the SAT does come back, they're going to offer it every single week instead of once a month, so that all of the big rush students who need to take it can all get it done. Most colleges have said they're just going to waive the requirement for this upcoming school year in case you can't get it in time, which is probably like the smartest thing to do. And when it does come back, whatever that like first testing week is, if they canceled on you, like if you had a SAT set up and it ended up getting canceled because of the shelter-in-place orders, everybody who had a test registration from then will be given first priority for testing that week back. But for right now, that's about it. Are there any questions on that stuff? No? Okay. Nonetheless, let's go ahead and get started. So what we want to do is we want to take this system of 3 equations and we want to rewrite it as an augmented matrix. And then we want to use row operations to solve for the intersection of these 3 planes. So what does my augmented matrix look like? Anybody?
Two, -1, 1.
Yeah, and I'm really only interested in asking for help with this first row, so it's got to be 2, -1, 1, and notice that doesn't exactly match the way that the equation is written on up top. 2x plus z minus y. Keep in mind that this isn't just the numbers pulled off of here. This is meant to represent the x coefficient, the y coefficient, and the z coefficient in that order. So if it's not written exactly in that way, you will have to fix it before you put it into the matrix. Otherwise, you'll get the wrong answer out on the other side. With the 3 on the opposite side there. And so this is going to be 1x plus 1y. And how many z's are in that second row?
Zero.
Thank you. 0. Minus 1. And then this last row is pretty straightforward. 3, -1, and -2. Okay, so now before we start it off, I'm going to work it out in our calculator just so that we can look at that procedure one more time. And so that we know what type of solution it is that we are working towards. So in order to do this, I'm going to go to second matrix. I'm going to edit this matrix. Last time we had solved a very similar type of problem, and so the dimensions already are correct. This is a 3 by 4. And now all I have to do is put in the values, so it'll be 2, -1, 1, 3, 1, 1, 0, -1, 3, -1, -2, and 7. Now that that's done, I'm going to go back a menu. So I'm going to hit second matrix. I'm going to go over to math. And in order to solve this, that's the same as saying that I'm going to do row operations until this thing is in reduced row echelon form. ref is typically a more useful command than just ref, right? I'm going to hit enter. Oh, I am sorry. That shouldn't do that. Entry 3, 4 is 7. My mistake was I forgot to go all the way back to the top menu before I did anything. I went straight from the matrix back to matrix, so I apologize. So it should be second matrix from the top menu, math, and then we scroll all the way down to option B to get reduced row echelon form. Then I hit second matrix again so that I can specify that I want to do this to matrix A, close those parentheses, hit enter. And so if we look at this, the left-hand side can become the unit matrix. I'm sorry, the identity matrix, right? Which means that this problem is solvable. We're not going to get no solution. We're not going to get infinite solutions. And our answer should be the ordered set 1, -2, -1. And so I'm going to go ahead and go back to the notes and then plow through this set of operations as quickly as I can. So the first thing that I want to do is I want to eliminate these two x positions here in the bottom left corner. So to do that, I need a common multiple between 2 and 1 and 3. So that's going to be 6. And I want all of this to cancel out. So I'm going to multiply the top row by -3. And I'm going to multiply these next two rows by +6 and +2 respectively, so that we get -6, +6, +6 in that order. So this is going to give us, and hey, please do error check me as I go along, because like I said, I'm going to try and go a little bit quicker here. -6, +3, -3, -9. 6, 6, 0, -6, 6, -2, -4, 14. And now that I've lined up all of my 6s in that first column, I'm going to go ahead and to row 2 and 3, I will now add row 1. That was the point of making sure that those values lined up so that when I add row 1 to rows 2 and 3, the x coefficient becomes 0. So row 1, I'll just rewrite it immediately. It's not going to change. -6, 3, -3, -9. -6 and 6 is 0. 3 and 6 is 9. -3 and 0 is -3. Over here on the right-hand side, -9 and -6 will give us -15. And then row 1 plus row 3 will give us 0. 3 and -2 will give us 1. -3 and -4 will give us -7. -9 and 14 will give us 5. Okay.
Mr. Robinson, quick question.
Yes.
When you're doing this operation, does the first row always have to be negative and then the second and third positive, or can the second and third be negative too?
That's an excellent question. And this is what I'm about to say is generally true, not just for this specific case, but in all mathematics and in all science. Positive and negative are arbitrary. It doesn't matter. The fact that both exist, actually, yeah, that's a little too deep. Yeah, no, it doesn't matter. So you can make the first row negative, the second two rows positive. You can make this positive, both of these negative, whatever is easiest for you.
Okay, cool. Thank you.
So now this is our next target because our goal is to clear out this bottom left corner. So 9 and 1 means this bottom row needs to get multiplied by -9. So this is going to turn our matrix set into -6, 3, -3, -9, 0, 9, -3, -15, 0, 9. Oh, I'm sorry, -9, +63, -45. And the point of this is so that 9 can eliminate with -9. So now to row 3, I will add row 2. I'll let it linger there for a second so we can check it for errors and so that you can get it copied down before I move on to the next page. Or actually, you know what? I'm just gonna come up here and keep going. Yeah. So then the first two rows are exactly the same, -6, 3, -3, -9, 0, 9, -3, -15. And then when I add row 2 to row 3, this is going to give us 0, 0, 60, 60, and then -60. Okay, and that agrees with the answer that we got from our calculator because we can see right here that if this is 60 and this is 60, then this bottom row is pretty clearly z is equal to -1. And now I want to finish this problem out in a slightly different way that some of y'all might like, just because this is a technique that is technically described in the section in case you did the reading. But let's go ahead and check out what this current system of equations is at right now, if we were to rewrite it in terms of x's and y's and z's. So I got -6x plus 3y minus 3z is equal to -9. I have 9y minus 3z is equal to -15. And here's what this bottom equation actually says. 60z is equal to -60. So if I divide both sides by -60, this will tell us instantly that z is actually equal to -1. Is this okay?
Yeah.
Okay. So from here, I'm going to get the exact same final answer, but this is not in reduced row echelon form. This is in row echelon form. But from here, I can do a nifty thing called back substitution, where since I have z and this equation is only y and z, since I have z, I can take this, pop it in here, and get y. Once I have y and z, I can take both of them and pop them into equation 1 in order to get x. This is actually the exact same procedure as doing all the work to get reduced row echelon form. This is just a slightly different take on how to get that final answer, but this will always produce that final answer. And in case you want to look this up, this is called back substitution, mentioned in the book.
Mr. Robinson, can we do this system?
Yeah, totally, yeah. Now, back substitution, honestly, it's only cool for 3x3s, which is why I didn't put it in the notes initially. So, like, personally, if I'm solving linear systems, and that sounds dumb, but physicists are constantly solving linear systems. If it's 2 equations, I just do substitution. Like, that's not fancy enough for me to get into matrix land. If it's a 3x3, I normally do this matrix stuff up to this point, and then I back substitute it. If it comes to anything bigger, anything that's 4x4 or higher dimension, that's when you definitely want to do row operations all the way until you're in reduced row echelon form. Is that okay?
Yeah, okay.
Like, I show you guys all these steps with these simpler systems so that you can understand what the steps are, but like knowing that for a specific problem type that a specific strategy will be more or less efficient, that takes a lot of practice and like overview to develop that kind of knowledge. But anyway, since we have this system of 3 equations written this way, back substitution's real convenient. So now that we know that z is -1, I can say that, oh no, not red. 9y minus 3 times z, which we just established is -1, is equal to -15. So that means that 9y plus 3 is equal to -15. 9y is equal to -18. And so y must be equal to -2. There's that second value in our ordered triplet. And now finally, I can take y and z and plug them into that first equation, which is to say -6x plus 3 times -2 minus 3 times -1 will be equal to -9. -6x minus 6 plus 3 is equal to -9. -6x minus 3 is equal to -9 minus 6x is equal to -6, so therefore x is equal to 1. And so our ordered triplet by this work, by using back substitution, is 1 and -2 and 1, just like our calculator said, just like Gaussian elimination would give us.
Mr. Robinson,
Yes,
can you explain how you got z again?
I got z at this step. So once we had deleted the entire bottom left corner, as we are wont to do, we got that this equation right here, what the bottom row is saying, is that 60z, right? Because if we just read this, it's saying 0x plus 0y plus 60z is equal to -60.
Oh,
So
yeah.
from
So
here,
it's
before I
-1.
rewrote it, perfect.
It's -1.
Mhm.
All right, got it.
Cool, cool. Is all of this okay up through here?
Can you scroll up a little bit too?
Here? Or on that same
No,
page?
on the first page.
Yes.
Thank you.
Mm-hmm. Okay. Are y'all ready for today's notes then? Sorry that we're getting started late. If we can't finish everything tomorrow and have a workshop, I'll extend stuff a day. I just didn't want to miss a whole day of stuff just because I am running on no sleep. Typically, if we were still physically going to school, I probably would have taken today off with the way I felt, but luckily, since I'm at home, I can just teach these morning classes and then take a nap. Today, we're going to talk about section 9.7. Today, we'll be talking about solving matrices with inverses. Luckily, I laid down some of the foundation of the notes for this section, so I'll be able to skip over a bunch of it. Or not skip over it, it's stuff that we talked about early, because if you notice in the notes, or if y'all read out of the book, the other section doesn't actually talk about the identity matrix. It's introduced in this section, but since we already have some idea of it, since we already have some idea of what the identity matrix is, it will make this set of notes a little bit quicker. Today we're talking about solving matrices with inverses. So this is a wacky thought, but last week when we were talking about matrix operations, what matrix operations did we establish?
Identity matrix.
So that's not an operation, that's an object, right? So that's a thing that we can do math with, but an operation is when we take two mathematical objects and we somehow smush them together, right?
Oh, right. So, addition, subtraction, multiplication, I guess.
Yeah, that's perfect. So if you notice last week, we have defined matrix addition. That's straightforward. They have to be the same size, and we add the corresponding entries. We also defined subtraction. And that's exactly the same thing as addition. They have to be the same size, and we subtract the corresponding entries one by one. And we also have multiplication. When it comes to multiplication, we have two different kinds, right? we've defined matrix addition, subtraction, and multiplication of the scalar and matrix form. And again, I'm only actually interested in matrix multiplication for a bunch of different reasons. And even for matrix multiplication, we have rules. The number of columns of the first matrix needs to be equal to the number of rows of the second matrix. If they're the wrong size, you just can't do it, right? And if you think about the rules of arithmetic, we have 3 of 4, but which one are we missing?
Division.
Yeah, division. Division is problematic. Notice here that very notably, there is no matrix division. There's literally no such thing. In this section, what we're going to talk about is how can you get close to that? How can you approach the idea of matrix division? The closest thing that we have is multiplication of the matrix inverse. So before we talk about how to build or construct the inverse of a matrix, let me give you kind of what it is that I'm talking about, right? And this right here, what I'm about to say, is not a one-to-one analogy, but this is just something that it is kind of analogous to, right? So analogy. Let's say that I have 4x is equal to 8, and I must solve this problem without doing division. So instead of doing division, I'm going to multiply both sides by an inverse, and the inverse of multiply by 4 is divide by 4. So I'm going to multiply both sides by the inverse of multiply by 4. And now I can multiply straight across, which gives me that 1x is equal to 8 over 4, which tells me that x is equal to 2. So the analogy here is that I have some multiplication. I'm saying, hey, take x, multiply it by 4. And so to get rid of that multiply by 4, I multiply by 1/4 also, knowing that these two will cancel in their product and eliminate themselves on the left-hand side of the equation. Here's why I talk about this. Here is the definition of the inverse matrix. The definition of an inverse matrix. So I have my normal matrix A, and when we write about matrices, we use capital letters just because lowercase letters typically represent standard variables, right? And so when I say capital letter here, I'm going to give it an exponent, but that doesn't mean the normal thing that the exponent -1 means. So the inverse of matrix A is A raised to the -1. But if I were to take a number and raise it to the -1, that just means simple reciprocal, right? So 3 to the -1 is just 1/3. This -1 is a lot more like the -1 that accompanies a sign in inverse sign, where it doesn't mean just, hey, do 1 divided by that thing. It means that this and this will eliminate each other. And here are the properties of the inverse matrix. Here's kind of what defines how this thingy behaves. A times A inverse is equal to A inverse times A. And this is crazy because last week we talked about the fact that normally, right, in general, matrix multiplication is not commutative. That is to say that A times B is not going to be equal to B times A necessarily. Not only can it give you different values, like if I had 2 matrices and I multiplied them, AB would be different than BA, but sometimes one of those is possible while the other is impossible. If I had a 2 by 3 and we were going to multiply that times a 3 by 3, 2 by 3 times 3 by 3, that works. But if I were to change the order, you are literally not allowed to multiply a 3 by 3 times a 2 by 3. because those inside numbers, they don't allow it. However, when you multiply a matrix by its inverse, both of these products are exactly the same, and even more important, both of these products will give you back the identity matrix. Is this okay?
Yep.
So the definition of an inverse matrix is it is some matrix that I can multiply by another matrix such that these two values will cancel out entirely, and the only thing we get back is the identity matrix. And the nice thing about the identity matrix is, like, just like here in my little analogy, multiplying 1 by x doesn't affect x, so I could just throw the 1 away. Multiplying some matrix by the identity matrix does not affect that matrix, so once we get this down to the identity matrix, we can just throw it away. So very similarly to this little analogy on the side where I use numbers, consider the following example with matrices. Let's say I make my augmented matrix, right? I take some system of linear equations, and what we're turning it into each time is matrix A multiplied by matrix capital X, which was our little column, right? This isn't the letter X. It was our column made of X and Y, or if it's a 3 by 3, it's made of X and Y and Z, or if it's 4 equations, it would be made of W, X, and Y and Z. And we're saying that this coefficient multiplied by this column is equal to another column of values, B, right? And we do row operations until this guy is the identity matrix, and then this column becomes our answer. However, here's a way quicker way that we could get our answer. If we knew the identity matrix, the inverse matrix for matrix A, here's what we can do. So everything above this line is just the definition, and then here's the motivation for why we care about inverse matrices. If I multiply both sides by the inverse matrix A, which I can do, matrices are like any other mathematical object. So long as I do something to both sides of this equation, right, and I make no mistakes, this new equation will also be true. I can do A inverse times A times X is going to be equal to A inverse times B. All I did was I multiplied both sides by A inverse, just like in my analogy. I identify what I have going on that's holding my variable hostage, and I multiply both sides by its inverse. Now, the point of this is that, well, A inverse times A, that's defined. That will give me back the identity matrix. So then the identity matrix times our variable column will be equal to A inverse times B. The identity matrix times any matrix, it doesn't matter what size it is, will always just return back that matrix. So this will tell us immediately that X, Y, Z, whatever this column of variables is, will be equal to A inverse times B. So here's the whole motivation. Here's what makes inverse matrices special. If we have it on hand, we can solve for X, Y, Z, whether or not that's present in the question. We can solve for our unknown variables in our linear system by a single step of matrix multiplication. Instead of doing all of those operations in order to get the answer, if we have the inverse matrix on hand, we can just multiply it, and we will get that answer back right away. Okay. Are there any questions on the notes up to here, just on like what an inverse matrix is, why we care?
Not really, no.
Okay. And now, and I don't want y'all to take, don't look for any special pattern in these two matrices, because the pattern of identifying inverse matrices is identifying inverse matrices is not trivial. This example is set up to work. So for example, show that A and A inverse are inverses, where A is going to be equal to the matrix 1, 5, -2, -9. And what I am supposing to say here is that inverse of matrix A is -9, -5, 2, 1. But what I'm asking you to do is show that they are inverses. So guess what it is I'm asking you to do? What operation?
Multiplication.
Please multiply, yeah. And when you're asked to show that two matrices are inverses, it is sufficient to do one step of matrix multiplication. But I guarantee when you all go to college, you'll be asked to do it both ways. Show that both A times A inverse and A inverse times A, both of those will give us I. So we'll be doing it both ways. If these are true inverses, both versions of this product will give us back the identity matrix I. So let's go ahead and get going. So this one is telling us to do 1, 5, -2, -9, multiplied by -9, -5, 2 and 1. And when we multiply matrices, we take the rows of the first matrix, multiply them by the columns of the second matrix. And so for this first entry, it's going to be 1 times -9 plus 2 times 10. For the second entry, it's going to be 1 times -5 plus 5 times 1. For this bottom left entry, it's going to be 18 minus 18. And then for this bottom right entry, it's going to be 10 minus 9, which of course, if our arithmetic doesn't fail, gives us 1, 0, 0, 1. Right there.
And that shows they are inverses, correct?
This shows that they are inverses. However, to be pedantic, technically, it has to work both ways. Now, because this is a 2 by 2, you couldn't actually invent a problem where it worked one way and not the other. But there are cases with 3 by 3 matrices where one matrix times another matrix can give you the identity matrix, but swapping them may not give the same result.
Right.
So technically, you got to do it both ways. And if I ask you to do this on the test, I will be explicit in asking you to do it both ways. You won't have to guess. And so here's our second product, -9, -5, 2 and 1. And 1 and 5 and -2 and -9. Now keep in mind that matrices are not like numbers. Just because 3 times 4 is 12 and 4 times 3 is 12, that means regular multiplication is commutative. However, this is the only case in which matrix multiplication is. So it is worth working out both ways. And once again, multiplication here. It's going to be -9 and 1, gives us -9. 2 and -5 is going to be +10. -9 and 5 will give us -45. -5 and -9 will give us +45. And again, look, the work isn't the same, right? The work disagrees, which I think on its own shows that this is not necessarily commutative. Nonetheless, bottom left corner, 2 and 1 is going to be 2. -2 and 1 is going to be -2. And then bottom right corner, 5 and 2 is 10. -9 and 1 is -9. And even though the work is different, this will still give us back 1, 0, 0, 1. And so, because both of these products work out to return back to us the identity matrix, this is sufficient to show that these two matrices are true inverses of each other. So here's how this can be useful. Here's where we're going with this. And I guess I will have to just wait until tomorrow to assign the homework, because I won't be able to finish the notes today. I'll get us to a good stopping point, but we will have to go over the technique that lets us build an inverse matrix tomorrow, sadly. And so please consider the following. Let's say that I had the system of linear equations, x plus 5y is equal to 11. And I also had the system negative 2x minus 9y is equal to negative 20. And so I want to solve this, but I want to do it hyper efficiently. I want to do it in a way that I've never done it before. What do you notice about that left-hand side of the equation?
There's no coefficient in front of x.
There's
The
a coefficient
top
in front
one.
of x, it's 1.
I mean, yeah, 1, right. So all you need to do is multiply it by 2.
No, we're not doing elimination. What do you notice about this system of linear equations? Look at the notes that we did up above.
It's the matrix that you wrote.
Yeah, these coefficients right here, these are the matrix that I wrote, matrix A. 1, 5,
yeah.
negative 2, negative 9, 1, 5, negative 2, negative 9. So let's go ahead and see if our technique of multiplying by an inverse works. Let's see if that will actually solve this system of equations for us. So I'm going to take this guy and I'm going to rewrite it as an augmented coefficient matrix. And so this is 1 and 5 and negative 2 and 9 multiplied by the implicit column of variables x, y, and this is going to be equal on the right-hand side to 11, negative 20. And so, and again, I'm going to do this off to the right because what I'm about to do, you don't normally show this work. This is just like proof stuff, right? I'm going to say that this is actually ax is equal to b. And so if I want to solve for x, right, my column of variables, I multiply a inverse into both sides. A inverse a into x will give us a inverse into b. These two cancel because that produces an identity matrix for us. And so a way to solve this should be that x is going to be equal to a inverse into b. So let's see if that's true. If this side work is correct, all I have to do to solve this is multiply both sides by the inverse. So x and y should be equal to a inverse, which we established up top, negative 9, negative 5, 2 and 1, into matrix B, which is our right-hand constants, into 11, negative 20. And so this is telling us that x, y, by the laws of matrix multiplication, should be equal to this row and this row, just times this column. And is this multiplication even allowed? Do the dimensions work out? What size is this?
2 by 2.
And this guy here is
2 by 1.
2 by 1. These twos cancel, which means that, hey, we are allowed to do this. And our final answer will end up being a 2 by 1, which it better be considering this is a 2 by 1. And so I'm going to go ahead and do this now. So this is going to give us row by column, negative 99 plus 100.
Mr. Robinson,
Yes.
sorry to interrupt, but how'd you get from 1, 5, negative 2 and 9 to negative 9, negative 5, 2 and 1?
I only know to use negative 9, negative 5, 2 and 1 as my inverse for A inverse because in this example up above, we took a step to establish that they are true inverses. So up here, I show that this matrix and this matrix are inverses. I haven't shown you how to build this yet, but that's what we'll do tomorrow. So down here, I'm using that fact.
Oh, all right, I
This
got
left
it.
side, oh, got it?
Yeah, I got it. Thanks.
Okay, yeah. So if AX is B, hitting both sides with the inverse, we'll get rid of that stuff on the left-hand side, telling us that X is equal to A inverse times B. So we're going to get the answer to this system of equations with no row operations, just multiplication. Second row, right? So here we had 11 and negative 9 gives us negative 99. Negative 5 and negative 20 gives us positive 100. So now I'm going to do the second row multiplied by this column. So it's going to be 2 and 11, which is going to be 22, 1 and negative 20, which is negative 20. And this tells us that our answer is 1, 2. That x, y is 1, 2, which is to say a more elegant way of writing that is x, I'm tired, leave me alone. That our ordered pair for the answer x, y is 1, 2. Now, it's really easy to check to see that this is correct, right? So let's go ahead and look at the system of equations that we were solving. 1 plus 5 times 2, that's 11. Negative 2 minus 18 is negative 20. This is obviously the correct answer here. And we solved for this without doing a single row operation, just by jumping to the inverse and multiplying by it. Is this okay?
Yeah, looks good.
Cool. Are there any questions up through here? No?
Mr. Robinson, yeah, quick question. Will there ever be a scenario where inverse A and B cannot be multiplied, so you can't get the final answer?
No.
They'll always be able to multiply?
That's a really interesting question. You are correct in asking a conditional statement, right? Like if, then. However, when it comes to this method, and we'll talk about this more tomorrow, all of the ifing and thenning about when this works, when you're allowed to do it, when this will give us a real answer, it all depends on whether or not a matrix has an inverse. Basically, if a matrix has an inverse, then this technique will work. However, as we're going to find tomorrow, not all matrices necessarily have inverses.
Okay.
The same way how like you can't divide by 0, so sometimes dividing by 0 doesn't work. There are cases where a matrix will force us to divide by 0, and as a result, we cannot invert it.
Okay.
Okay. So here is the last item of notes that we'll jot down today. And don't worry, we're not going to do any math. This is just real quick, like basically an outline of what it is we're going to do tomorrow. Here's how we construct an inverse. So general construction of an inverse. And just full disclosure, this is the technique of building an inverse that always works. However, if you are so motivated, you can look up shortcuts that will do the same thing but quicker for specific size matrices. So there is a way quicker way to do this for a 2x2. There is a slightly quicker way to do this for a 3x3. However, doing this for a 4x4, you will always have to do this general approach. All that you have to do in order to create the inverse of any given matrix is step 1, attach your matrix to an identity matrix of the same dimension Then we are going to use Gaussian elimination. Oh no, that's a name. That gets a capital G. Use Gaussian elimination in order to produce reduced row echelon form on the left once the left-hand side is the identity matrix, then the right-hand side has become the inverse. So the way that one could produce the inverse of matrix A that we just showed in the previous example was the inverse, right? Because I didn't tell you where inverse A came from. I was just like, hey, here you go, please multiply, right? The way that this is done is you take the matrix that you have, you attach it to the identity matrix I of the same dimension, and then we do row operations in order to turn these ugly digits on the left into the identity matrix. And on the right-hand side, by the time we're done, The identity matrix that was over here will basically keep track of all of the swaps that we made and the changes that we did in order to get the left-hand side to be I. And after the left-hand side has become I, the right-hand side will have become the inverse. Tomorrow when we come in, we'll do this with an actual matrix. We'll go through this procedure in order to build an inverse by hand. And then we're going to talk about a really, really, really important idea in terms of matrices called the determinant. There is a magical number that you can calculate for a matrix. You can take all of the numbers in a matrix and turn it into one number called the determinant, and that determinant can tell us all sorts of information about the character of a matrix. Are there any questions today about all of this stuff? Or the SAT or anything in general? No? I'm going to put the homework up for this section. I'm just going to put the whole thing up, but know that it won't be due until Wednesday night, since I didn't get to finish all of the lecture today. And as a result, of course, we'll, I don't know if I'll have to move a lesson. I'll kind of leave that up to you guys. I'll ask you how you're feeling about this tomorrow. I'd like to get through 2 sections this week, but if that doesn't happen, that's okay, just because the stuff about the determinant, real big, real important, especially for those of you going into physics and engineering. There's a ton of stuff that you can learn about a physical system by taking its determinant.
Mr.
I'll talk about those applications next section. Yeah, what's up?
Sir, when will the chapter test be?
Oh, so this chapter has 8 sections, so it would be next week sometime after we're done with review. Also, just so y'all know that unlike most chapter tests, there will be no review questions since we did the first half of this chapter before break. And if you think about it, this math that we're doing is actually the same, right? We're just solving for where lines meet. We're just representing these ideas differently. So the chapter test will only be on the 4 sections that we did since we came back, so that y'all don't have to go back to 3 weeks ago and review a bunch of really old stuff.
Nice.
Oh, okay.
Yeah, this is a really, really long chapter. So I'm basically treating it as 2 tiny chapters. Is this okay? Are there any questions on that stuff?
No, sounds good.
No, okay. Well, y'all have a very nice day. Sorry to start late and have us go over by a little bit. And whenever I pick up my cat, I'll post a picture that he's okay to classroom, since I wouldn't normally, you know, let information about my life like that out, but yeah, man, I'm tired. That cat freaked me out, dog. And cat surgery is expensive, and I'm real glad I have cat insurance. Peace, y'all.
Thank you,
See you,
Mr.
Mr. Robinson.
Yep.
Bye, everybody.
Oogie feels better.
Oh yeah. Hopefully
Mr.
the
Robinson,
surgery
what
went
happened,
good. He's a dummy, and he ate a piece of string about this long, which is a thing he's done before. And normally, if you have him throw it up, it's okay. But we got him to the vet, and he didn't throw up in time, so they actually had to do surgery and remove it from his guts.
Oh, Jesus.
Because this is true of humans too. If you eat something that will get knotted up and tangled, it can actually cause knots and tangles in your intestines, which can cause blockages, which cause all these down the line problems. So they had to like open him up and remove it. So today he's recovering from surgery. Yesterday was Sunday during the pandemic, so all of the vets were closed, and I had to take him like an hour out of town to a vet way up in the mountains. But they were able to get him taken care of, luckily. And it's wicked expensive, but luckily we have health insurance for our pets through a major company. So instead of it costing like the same as the down payment of a car, it'll only be a couple $100.
Nice.
Yeah, when you get a pet, some people think it's like unnecessary. I highly recommend that you get pet insurance if you can, mostly because one of my homies who's a doctor, like leg surgery for their dog was $9,000, and if they just had insurance, it only would have been like $300 or $400. Anyway, y'all have a nice day.
Yeah. See you.
Peace.